Ever looked up at a giant jetliner streaking across the sky and wondered what unseen magic keeps it humming mile after mile? It's far more sophisticated than just, a big gas tank.
Oh, absolutely. Way more complex.
So today we're taking a deep dive into the intricate, often invisible world of aircraft fuel systems.
Right.
Our mission, to sort of pull out the most important nuggets of knowledge about how fuel is stored, delivered, and managed. Ensuring safety and efficiency from takeoff right through to touchdown.
It's about unraveling that sophisticated engineering that turns, well, a simple liquid into sustained flight.
Exactly. So whether you're just curious about how planes stay up or want to truly appreciate the genius behind them, you're about to gain a whole new understanding of this vital part of aviation.
It truly is a symphony of engineering disciplines, all converging to manage one of the most powerful and potentially volatile elements on an aircraft.
Yeah.
Every single component has a critical role, and the system is constantly adapting.
That's a great way to put it, a symphony. So let's start at the very beginning. Where does all that fuel actually live? Most of us picture traditional tanks maybe, but aircraft designers got really clever here, didn't they?
They absolutely did. Modern aircraft ingeniously integrate fuel tanks directly into the aircraft structure.
Into the structure itself.
Yeah, primarily within the wings, and sometimes even into the horizontal stabilizer at the tail.
Wow, okay.
This smart design does double duty. It maximizes fuel capacity where space is naturally available, and it minimizes added weight.
Right.
You see, during manufacturing, these wing sections are meticulously sealed. They use these special two-part sealants, not just along the edges, but around every single rivet and inspection opening.
Every single one.
Every single one. It's a painstaking process, really, to ensure zero leaks and protect against erosion from, high-pressure fuel moving around inside.
So the wings aren't just for lift, they're also giant fuel reservoirs. That makes a lot of sense for efficiency. But, okay, with fuel sloshing around inside these structural components, the materials chosen must be incredibly important. Aluminum alloys are essentially the backbone of aircraft, right?
They are indeed the unsung heroes. Aluminum alloys are paramount due to their incredible strength-to-weight ratio. But while we rely heavily on aluminum, specialized non-ferrous metals also play crucial roles. Titanium, for example, you'll find that in high-stress areas like landing gear brackets.
Okay.
And then there's nickel. You might not think much about it, but in the harsh, corrosive environment of a fuel system, nickel's exceptional resistance to corrosion is, well, it's what prevents tiny, unseen leaks from turning into catastrophic failures over years of service.
You just mentioned corrosion. That sounds like a persistent enemy, especially inside a fuel tank.
Yeah.
How do engineers even begin to tackle something like that?
Corrosion is a huge concern, yeah, because it can compromise structural integrity over time. One common and insidious type is galvanic corrosion. Yeah, imagine a tiny unwanted battery forming inside the tank. When two different metals, say zinc and copper, are in contact and exposed to a conductive liquid, which fuel with even a trace of water can become, they create an electrical current.
Right.
Even a tiny scratch in the paint surface can kickstart this process, slowly but surely eating away at the metal.
A tiny battery eating the plane from the inside. That's quite a visual. Are there other types of corrosion that aircraft designers lose sleep over?
Absolutely. Magnesium alloys, for instance, are prone to their own specific type of corrosion if not properly protected.
Okay.
And copper alloys can suffer what's called dezincification. Imagine brass, which is an alloy of copper and zinc. Dezincification is like the zinc slowly leaching out, leaving behind a porous, weak copper structure that can easily fail under stress.
So given these relentless enemies, what are the defenses? What kind of armor do they give the metal?
Well, engineers employ several clever protective measures. One common technique is anodizing.
Anodized.
Think of it as growing a super tough, microscopic armor plating on the surface of the aluminum. This layer of aluminum oxide dramatically improves resistance to wear, corrosion, and even high temperatures.
Interesting.
Another smart trick is cladding. This is where thin layers of pure aluminum are rolled onto stronger aluminum alloy sheets. This pure aluminum acts as a sacrificial layer, kind of corroding first to protect the underlying structural alloy.
Sacrificial.
But then there's a specific issue with titanium called hydrogen embrittlement. This is where contact with acids or hydrogen at high temperatures can cause delayed cracking even after the initial exposure, severely weakening the component.
It sounds like a constant uphill battle for traditional metals. It makes me wonder if there's a completely different approach, maybe a whole new generation of materials offering a fresh defense. Are composites changing the game here?
Definitely. High-performance composites are increasingly vital precisely because they address many of these challenges. We're talking about reinforced plastics, essentially a plastic resin matrix combined with super strong fibers like carbon fiber or fiberglass.
Okay. Their strength-to-weight ratio is incredible, and they are inherently resistant to corrosion. I mean, a composite part can be up to 25 times lighter than a metal equivalent, while being just as strong and durable.
25 times lighter.
Yeah.
Fiberglass, for example, first found use in radomes and is impervious to strong acids, non-corroding, and non-burning. Nomex honeycomb is another marvel, offering exceptional strength to weight and resistance to moisture and fire.
That truly sounds like a game changer for longevity and weight savings. But even with the best materials, fuel itself is a volatile substance. How do they prevent accidental ignition inside those wing tanks?
This brings us to a critical safety system, the fuel tank inerting system, often called OBDGS.
OBGGS.
Or IGGS sometimes. It's essentially an onboard nitrogen generator. Its crucial role is to displace oxygen in the ullage, that's the flammable gas space above the fuel, with non-flammable nitrogen.
So pushing the oxygen out.
Exactly.
Yeah.
By reducing the oxygen concentration, it prevents any potential ignition source from sparking a fire, essentially making the fuel tank environment inert.
Inert. That makes sense.
Okay.
That's a fantastic overview of the foundation. Once the fuel is safely stored and inerted, it still needs to make its way from the wings to the hungry engines. How does it navigate its way through the aircraft, accommodating all the vibrations and flexing that happen in flight?
That's the job of the fuel highway,
Yeah.
an intricate network of rigid pipes and flexible hoses.
Right.
Those flexible hoses are especially crucial because they can absorb the constant vibration and flexing of the aircraft structure without fatiguing and failing.
Okay.
Installing these pipes and hoses is a precise art. They're cut to exact length, deburred to prevent stress points, and positioned with really tight tolerances, razor-thin margins from critical control systems.
The clearances are key.
Absolutely. Even a millimeter too close could lead to chafing, which over thousands of hours of vibration could spell disaster.
I can imagine how important it is for those flexible hoses not to twist during installation.
Absolutely paramount. Twisting a flexible hose during installation can weaken it significantly. Maintenance crews use ley lines or sometimes a visible braid pattern on the outer cover to ensure it remains untwisted when they tighten things up.
Like a guide.
Exactly. Connections also vary, from flared and flareless fittings, which demand precise lengths and meticulous inspections, to self-sealing couplings. And a seemingly simple thing like cleanliness is rigorously enforced at all stages of handling and maintenance. Contamination, even a speck of dirt, is a severe threat to these high-precision systems.
So, once it's flowing through this intricate highway, the fuel needs to be spotless and at the right pressure. What about filtration and monitoring?
Good question. Typical light aircraft use fuel filters consisting of a housing, a filter element, and a sediment bowl with a drain.
Okay.
Before every flight, technicians drain off any sediment and water that might have settled. A good seal when replacing that sediment bowl is absolutely critical. A tiny leak there could starve the engine of fuel.
Right, undersupply.
Precisely. Fuel pressure itself is constantly monitored using flexible diaphragms connected to sensors or pressure sensors, providing immediate indications to the flight crew. You want to know if your engine's getting enough to drink, essentially.
Yeah, you definitely do. It's all about ensuring a steady, clean flow. So, if the fuel is clean and at the right pressure, how is its flow managed and distributed, especially in larger, multi-engine aircraft?
Well, electrically actuated fuel valves provide precise control over fuel flow. In multi-engine aircraft, cross-feed systems are a prime example of this precision.
Cross-feed.
Yeah, they allow engineers, or rather the system, to feed any engine from any fuel tank. This flexibility is vital for balancing fuel, managing emergencies, or optimizing weight distribution. All while ensuring independent tank outlets for each engine, mind you. Then there's the fuel jettison system, often called a dump system.
For emergencies.
Exactly. Its purpose is to rapidly reduce the aircraft's weight below its maximum certified landing weight in an emergency, like an unplanned return to the airport right after takeoff. It's operated from the flight deck and includes an automatic shutoff.
So it knows when to stop.
Right. But not all aircraft have this system, typically only those whose maximum landing weight is significantly less than their maximum takeoff weight.
Gotcha. You mentioned contamination earlier as a threat. What are the most common culprits lurking in aviation fuel?
Oh, the unseen threats of contamination are quite diverse. You're looking at solids like iron rust, scale, sand, dirt, even lint.
Lint? Really?
Yeah. And then there's sludge, often from bacterial action. Water is a very common issue. And with turbine fuels, you also worry about surfactants and microorganisms.
The bacteria in the fuel?
It can happen. So during maintenance, fuel sampling is a routine and vital procedure. Samples are collected in glass jars from drain valves at specific points and meticulously inspected for free water, sediment, and microbiological contamination. It's like a daily checkup for the fuel's health.
And if they suspect water, how do they confirm it quickly and accurately?
They use a hydrokit test. It's a chemical test where a white powder in the kit changes color, usually to purple if water is present, gives a clear, positive identification.
Simple but effective.
Very. And if excessive contamination is found, all the fuel must be drained, the tanks cleaned, and then partially filled with clean fuel and redrained until all subsequent samples come back pristine. You simply cannot take chances with fuel quality.
Absolutely not. That's a rigorous process to ensure fuel purity. Let's move on to the grand finale.
Yeah.
Getting that perfectly clean, pristine fuel into the engines and ensuring it combusts correctly.
Right. This is where the fuel system truly integrates with engine performance. Its critical role is to deliver fuel in the correct quantity and condition for engine start and sustained combustion.
And the challenges.
The challenges are particularly amplified during rapid acceleration. The system has to provide enough energy without creating an over-rich mixture, which is essentially too much fuel for the available air.
Too much fuel.
Yep.
Bad.
Very bad. That can lead to a compressor stall, where the engine chokes and stops sucking air properly, or even a flame out, where the combustion just extinguishes completely mid-flight. Not something you want.
Definitely not. So, how exactly does the fuel get into the combustion chamber to burn so efficiently, avoiding those scary scenarios?
That's the precise job of the fuel nozzles. They atomize or vaporize the fuel, turning it into a fine mist or vapor for efficient burning.
Like an aerosol can.
Sorta, yeah, but much more controlled. Dual-line duplex nozzles are common. They have primary and secondary discharge orifices that create different spray patterns for various engine operating conditions. Think of it like a shower head that can change its spray depending on how much water pressure you have.
Okay.
A more advanced design is the air spray nozzle. This actually mixes primary combustion air with the injected fuel before it even burns. This reduces rich concentrations in smoke, and because it requires lower atomization pressures, it allows for the use of lighter pumps.
Clever. That's a lot of precision engineering just for getting the fuel in. Who or what orchestrates all of this, making real-time adjustments?
This is managed by increasingly sophisticated fuel control units. Early systems were pneumatic mechanical, suitable for smaller engines. Then came hydromechanical.
Right.
And now we have advanced hydromechanical electronic, or the big one, full authority digital engine control, or FADC systems.
ATTC. Heard that term.
FADT is essentially the engine's brain. It continuously monitors a multitude of inputs, things like air data, ambient temperature, static and total air pressure, to automatically control fuel flow, manage igniters, and operate valves.
It's doing everything.
Pretty much. It ensures that commanded thrust is maintained without exceeding crucial limits like exhaust gas temperature or EGT. FADD systems are so clever they can even adapt their control modes based on changing conditions or component failures.
Speaking of changing conditions, fuel temperature sounds like a big factor. Too hot or too cold must present its own set of problems.
Absolutely. Monitoring fuel temperature is vital. Fuel that's too cold can lead to ice crystal formation, which can quickly clog fuel filters.
Ice in the fuel line.
Exactly. To combat this, systems either activate fuel heat or require a reduction in engine power. This ties directly into engine ice protection systems as well, where hot bleed air from the engine compressor, say from the 5th or 9th stage, is routed to heat the inlet cowl leading edge.
To stop ice forming on the outside too.
Right, prevents ice buildup there, which could severely disrupt airflow and impact engine performance. It's all connected.
It's incredible how many variables need to be managed simultaneously. And then there's the aircraft's physical balance and flight, its center of gravity. How does the fuel system contribute to that?
This is a subtle but absolutely critical function. Center of gravity, or CG, control through fuel transfer.
Using the fuel's weight.
Precisely. The objective is to keep the aircraft's balance point within a very specific range. This helps keep the horizontal stabilizer, that small wing at the tail, as streamlined as possible, optimizing both fuel economy and overall performance.
Okay.
Computers use data like the aircraft's zero fuel weight, current fuel quantity, and fuel flow to activate valves and pumps, precisely transferring fuel forward or aft as needed to maintain that target CG.
So it's constantly adjusting.
Constantly, even in the rare event of a system failure, it can revert to an alternate mode, perhaps emptying a dedicated trim tank to achieve a safe CG.
Amazing. So with all these unbelievably complex operations, safety and meticulous maintenance must be absolutely paramount. What happens on the ground during fueling, for example?
Fueling is a highly critical ground operation, yeah. Because of the highly flammable and volatile nature of aviation fuels, non-negotiable precautions include having appropriate service fire extinguishers readily available.
The right kind, I guess.
Exactly. CO2 extinguishers are preferred for electrical equipment, using non-conductive nozzles, while dry powder, like sodium bicarbonate, is typically used for Class D fires, such as brake fires. It's not just about putting out a fire, it's about having the right tool for the specific job.
And what about comprehensive fire protection systems built into the aircraft itself?
These systems are layered and incredibly sophisticated. You have various types of heat and overheat detectors, thermocouple types that generate voltage proportional to temperature differences,
Okay.
continuous loop systems that sense a temperature threshold along the entire loop, and pressure-type sensors that actuate under high temperature or widespread lower heat. These are often combined with smoke and flame detectors, like photoelectric sensors in cargo compartments, adding another crucial layer of defense. It makes it incredibly difficult for a fire to go unnoticed or unchecked.
Layers of safety. After all this, how do they ensure everything remains in top condition and identify potential issues before they become problems?
That's where rigorous inspection and testing come in. Pressure tests are conducted at regular intervals after repairs, modifications, component replacements, or if any leakage is suspected, for the entire fuel system, vents, feed lines, transfer lines.
Testing everything.
Everything. These tests require meticulously clean test fluid and precisely calibrated equipment. Non-destructive testing, or NDT methods, are also vital. This includes things like ultrasonic or eddy current methods to detect tiny cracks around bolt holes and other stressed points, or using borescopes for inspections to examine inaccessible areas deep inside the system.
Like keyhole surgery for engines.
Kind of, yeah. And general maintenance principles are drilled in. Scrupulous cleaning of components, removing all swarf and dirt, using correct lubricants like special lubricants for oxygen systems, never petroleum-based, and diligently checking for any damage, corrosion, or security issues.
And what if damage or wear is detected? How is that managed without compromising safety?
Damage assessment is a very meticulous process. It involves identifying the maximum permissible metal removal, ensuring any depressions are smoothly saucer-shaped without sharp ridges, and crucially, avoiding contamination during corrosion removal. This means never using dirty abrasives or the wrong brushes, for example. Proper storage of components is also key, especially those with seals or non-metallic parts. They must be stored in conditions that prevent degradation, often filled with system fluid, and with all connections securely blanked to prevent leakage or dirt ingress. Flexible pipes, particularly PTFE ones, need special care to avoid kinks.
What an incredible journey through the unseen workings of an aircraft. From the wing itself acting as a fuel tank, to microscopic battles against corrosion, and the digital brains orchestrating every drop.
Indeed. We've journeyed through the sophisticated world of aircraft fuel systems, haven't we? From the ingenious way fuel is stored to the precise controls that atomize and deliver it to the engine, all while being vigilantly monitored for safety and optimal performance.
Yeah.
It's a complex, layered system designed for both incredible power and steadfast reliability. Truly one of aviation's silent marvels.
It truly is an invisible ballet of engineering, material science, and automation, constantly managing one of the most volatile substances on board. This deep dive reveals how much unseen, intricate work goes into the seemingly simple act of flight. It makes you wonder, what other unseen systems are tirelessly working behind the scenes that you'd love to uncover?